All right, so welcome back. Who of you already filled the vGates form? Who didn't yet? Okay. I'm going to give you a few minutes. That was a request made by VCTA that in some lectures we give you time. I'm going to give you a few minutes so you can do it now. So let's say until 25 past 11. Of course, there's no obligation, right? But just to make sure that you have a slot to do it. So normally you have a link in your email. You just need to look for vGates, WIEGETHS, and in your email you have a link, and all you need to do is click to fill. All right. So I think that the goal of Far-West ETH is to be at 40%. I think a few days ago there were at 25, and the more of you feel it, the more accurate and representative is going to be. All right. So let me switch over to the slides. Even if you're not completely done, you can just close again and come back. It's all saved. Okay, so let's continue. So we were at the TF-IDF, which is absolutely central to what we are doing right now, right? It's this idea of having the term frequencies, which is bidimensional, term and document, the inverted document frequency, log of n over the document frequency, which only depends on the terms, and then we just multiply like this, and we can compute a score by summing over the relevant terms, the terms in the query. In fact, it's the same thing we already did with the zone search with the weight vector and the occurrence vector. So the occurrence vector S here is implicit. That's basically 1 for the terms in the query and 0 for the others. But in this case, I just put the 3 terms that have a 1 and didn't display the others. And the equivalent of G would be the TF-IDF things that you have in here. That would be the equivalence. And again, what we do, just like for zone search, is that we sum over the TF-IDFs, but only for the terms that are in the query. That's the trick here, right? And in that case, we find 48 for document B and 31 for document A, which means that B comes first and A comes second. Now, we can tweak that, and I'll come back to that. We can renormalize by document size. There are many, many, many ways we can now tweak the whole thing, and we're going to start diving into this. Which brings us to the vector space model. I told you last time we are going to do linear algebra today, so linear algebra, here we come. Remember that we kind of already had vectors in the sense of vectors of Booleans for the Boolean information retrieval framework. Now we switch over to bags of words. What does it mean for our vectors? Well, now it's no longer Booleans, it's actually vectors of numbers, real numbers, non-negative numbers in that case specifically. But this is the change of paradigm. So again, until now we've been doing this, and now we have documents as vectors of numbers. Okay, and again, each number corresponds to the TF-IDF, so the multiplication of term frequency times log of n over the document frequency for every term, and the order of the numbers is arbitrary. It's really, you take some ordering of the terms, it doesn't matter which one, but then you do the same ordering for every document, right? So maybe the first 0 corresponds to information, 1.2 corresponds to ETH, and so on, but you just need to have the same mapping from the terms to the positions in the vector for all your documents. Who is with me? So far, so good? Who is with me? More recent? Okay, awesome. So we had, now if I represent it like this as a column, so we had sets of words as zeros and ones. Now we have the interpretation of sets of words like this. What is a vector with zeros and ones? Technically, it's the vertices of a hypercube. Who sees that? Take it in 2 dimensions, a square. You have 0, 0, 0, 1, 1, 0, and then 1, 1 is the one on the right, right? So D1 would be 0, 1, and D2 would be 1, 0, right? So it's just that this is for 2 dimensions. This is with 2 Booleans. If you have 3 Booleans, then you have a cube. And then, of course, if you have more, like in that case, that would be in 8 dimensions. So of course, it's hard to visualize, but this is basically one of the vertices of a hypercube in 8 dimensions, right? So this is the interpretation of these documents seen as vectors in Boolean information retrieval. But now that we see them as bags of words, we have actual non-negative numbers in there. So it means that now we are no longer restricted to specifically the vertices. In fact, what we are looking at, so again, we put the TF-IDFs by default, so we can tweak as I explained. We are in fact looking at the first quadrants or R to the power of M. So there, the number of dimensions is the number of terms, right? And we called it big M, right? The number of terms. So big M is the height of this vector. There's M, big M numbers in there, big M dimensions. And we are looking at the first quadrant of R to the power of M. Why first quadrant? Well, it's because it's non-negative. We don't have any negative numbers. So all of these vectors will be in here, but not here, not here, not here, right? I put them as dots, but it's implicitly, this is the vector, right? This would basically from the origin to here. Who agrees with that? Awesome. So this is now the representation of bags of words. So I can put my million or billion documents in my collection, and I can get billions of points in here, in that first quadrant, billions of points. Now, this is a representation of my collection of documents, right? I dropped the books and the actual content, and I'm left with this vector space of dimension big M and big N dots appearing in the first quadrant. So far, so good, right? And we can also think of them from the origin, right? I can either view the points or I can view them as the arrows from the origin. Okay, now if I write it, there's many ways of denoting vectors. You can put an arrow on top, you can put it in bold, and so on and so on. But this is again the reminder that there's M dimensions. So there's x1, x2, all the way to xm. Here I use numbers as subscripts. You could also use the terms themselves, right? You could have X information, X retrieval, X ETH, and so on, right? But if you have a specific ordering, then X1, X2, all the way to XM. Now, what can we do? Well, it's actually cool because now that we have a vector space, we can actually play with it and do vector space things with our vector space, right? So what's the sort of things we can do now? For example, we can compute the norm of a vector. I can take a document and compute its norm, right? It's just the sum, the square root of the sum of the squares. Now we are coming to what you suggested earlier, the notion of renormalizing, and you as well. We can indeed renormalize over the size of a document. So I said there's multiple ways of considering the size. Could be the size in bytes, number of words, and so on. Or it could be the Euclidean norm of the document seen as a vector in the bag of words model. Okay, so that's the Euclidean norm. Normally, you're already familiar with that. And now that I have the Euclidean norm, I can renormalize my vectors. It means that I can take a document D1, and if I divide it by the norm, by the Euclidean norm, I can project it technically on the unit sphere, right? Well, on the first quadrant part of the unit sphere, and I get all my documents projected to that sphere, right? It's almost holographic, fancy mathematical terms. So I just project all of my documents on that unit sphere. Who is with me? Still with me? Okay. So now, just to give you an intuition, what does it mean? As a thought experiment, take a document. Let's say, I don't know, the last Harry Potter, the 7th volume of Harry Potter. And then you copy it privately and copy it and copy it and copy it and 10 times over. And then you have the same book, but copied over 10 times. What do you think the vector is going to be if you take the vector of the original book and now the new vector? How do they compare the two vectors of the book and the deduplicated book? Who sees that it's technically just the same vector, but longer? Who sees that? Awesome. So basically, this is the meaning of renormalization. We basically compensate for the potential size of a book by just putting it back on the unit sphere. Okay? So if you do it with the documents, this is what you look like. You're just going to end up with numbers that are all between 0 and 1. You will no longer have anything greater than 1 in there. Okay? All right. And again, the Euclidean norm of the renormalized vector will be 1, meaning that the sum of the squares will be 1. If you do a bit of quantum physics, this is kind of what we do with the vectors as well in there. We love to renormalize them. And this is why you have this 0 plus 1 over square root of 2. It also comes from there. Okay? So what other vector spacey things can we do with our documents? Well, another thing that we can do that kind of is related to the Euclidean norm is the inner product, right? Now I can take two documents and I can compute the inner product. Now you're going to tell me the inner product of two documents? Yes, because these are vectors of numbers. So I can compute the inner product of vectors of numbers. And you might know the formula for that, which is the sum of the products of the coordinates. For every term you multiply and then you sum over the terms. So this is the inner product. And that gives me the angle between the two documents, right? It's the angle that they would form when taken from the origin. Now it's two-dimensional, but you have to imagine that in general, there can be more dimensions. That's my way of my computer to tell me, slow down, give the time, take the pace. All right. Now, the next thing we like to do, and if I bring back the renormalization thing, is that the angle between documents doesn't tell us much, right? The actual absolute inner product doesn't tell us much. If we really are interested in the angle itself, we need to renormalize. And technically, you know that the cosine of the angle is basically the inner product, but of the renormalized vectors. So if you project them on the unit sphere and then take the scalar product, then that's the cosine of the angle, right? It's going to be 0 in the case of if they are orthogonal, so the angle is pi over 2 or 90 degrees, and the cosine is going to be 1, so the inner product is 1 if the angle is 0. But then it means it's exactly the same document, or it's copied documents that looks alike. Okay, who is with me? Okay. Now you see something cool, because this is kind of a déjà vu here, because this notion of cosine, it tells us how similar two documents are, and it involves summing over the terms and taking the products. We've actually been doing that in the first hour many times. So now that shouldn't surprise you anymore, except that now it's really nice because we can just formulate it as the angle between the renormalized vectors corresponding to the documents in our vector space. Right. So this is really a very, very good way of saying how similar two documents are. So for example, if I take these two documents, the purple and the blue documents, if I renormalize them, I project them onto my unit sphere and I get these green documents, right? And now I can see they are very similar, these two documents, right? And if I take these two documents, then they are more different, right? Again, this is two dimensions here. Imagine with 500,000 dimensions is already a lot, 500,000 dimensions. Now, if you have two documents like these that are very similar on 500,000 dimensions, it really means they contain the same ratios of terms, these two documents. So they are very, very similar. You just don't know the order of the terms. But that we already said we throw away. Okay, so very similar documents, very different documents. So this cosine of the angle, it's called the cosine similarity, which is the inner product of the document vectors, tell us how close or how different two documents are. Now, here's the next cool thing. What about the query? Because the documents, that's nice, that's our collection. We put it all in there, we computed the numbers, we have our points in there, we can compute how similar the documents are. That's actually great. But now, how do we use that as an information retrieval system? Well, we need the query. What is the query? Well, technically, the query is not very different from a document, right? It's a much shorter document. Of course, you're not putting into a Google search box an entire novel. But technically, a query is like a document. So do you agree that if you take a query, you can also build a vector with the TF-IDFs, but as if the query were a document? Who sees that? Right? Treat the query as a document, compute the TF-IDFs. That gives you a vector. So now it means that if you have your collection in there, all the blue dots, if you have a query, that's the yellow dots, these are two queries. Imagine that you have query 2, Q2, that might be, I don't know, information retrieval ETH. And if I compute the vector of TF-IDFs, that's my yellow dot, Q2. And now executing the query means I want to find all of the documents that are similar to my query. So it means that I want a small angle, right? So for example, if I have this query right here, I need to look at the angle again. It doesn't matter how far away it is because we renormalize. But do you agree that D3 is a good result for Q2? And that D2 would not be a good result for Q2 because it's farther away in terms of angle. Likewise, Q1 would have D1 and D2 as good results. Who starts getting the intuition of that? Very good. So you see, we are looking for the documents that have an inner product as close to 1 as possible to the query, with the query. Renormalized, of course. Yes, we want to take the habit of this because the people on Zoom can hear you. You just need to give me a bit of time to adjust the volume. There you go.
To map a query to one of these dots in these in this vector space, do we just set 1 for every term requested in the query, or do we have a different number to make more sense of some other things?
It is a very good question. And in fact, you can do what you want. Thank you. In fact, you can do what you want, and there's many ways of doing that. You could do it, if you treat it as a document, what does it mean? It means you count the number of occurrences of every term in the query. Now, if it's a query, the typical one you type on Google, it's 1 typically. So you're going to have 1s and 0s, but renormalize with an IDF. You can choose to not renormalize to not multiply with the IDF. That's also something you can do. Then it's just 0s or 1s. You can also choose to not renormalize the query, right? But you can also choose to renormalize and treat it exactly like a document. Now, do you agree that who has ever pasted an error message into Google? You did it, right? So in that case, it wouldn't be 1. It can be multiple occurrences. But then again, it's really a decision that you make in your system. You can either say, okay, for the query, I don't care about the TF. I just put 1. For the documents, I do care. Or you might say, okay, no, for the query, I also care. If my error message has 5 times the same word, then maybe I want to give it more weight. So the answer to your question is, this is a parameter of the system that is within your control. You can choose. Right? And I will show you even the restaurant menu, and there's a clever naming system for all the tweaks that you can make to the system. It's called SMART, the whole thing. Okay, I'm going to remove the background noise because I know that it just makes this annoying noise. Okay. But for now, for my discussion, just assume the query is treated like a document, and we just do it as with a TF-IDF, a vector of TF-IDF, just like for the documents, right? Then I'll come back later to the fact that we can actually adapt. All right, so that's cool because now we have a retrieval system. We just take the query, put it in as a dot in here, and find all the documents that are close in terms of angle that are close to the query, and that's it. Who agrees we have a ranked information retrieval system now? Why ranked? Because I can rank the documents based on the angles. I start with the documents very close, and then I get farther and farther and farther. Okay, now here's the thing. It's good for the mathematicians, right? The mathematicians are happy because it's all happening on a blackboard or in our brains or in the beautiful world of mathematics. So for a mathematician, a vector space of dimension 1 billion or even infinite is no problem. But we are computer scientists and we want to put that in a computer. So now the problem we have is that we need to compute inner products in a vector space of dimension. So M is typically 500,000, if you want an order of magnitude. So 500,000 terms. And the number of vectors, so the number of documents, I don't know why I put D, normally it's big N that we call it, the number of documents, so big N. We have basically 1 billion vectors. So I basically have a query and I need to compute 1 billion inner products on vectors that have 500,000 rows. Can you imagine how expensive that is? Right, so this is a big deal in terms of implementation. Yes and no, because in fact, if you look closer to this inner product that we do between so I have the query vector on the left and the document vector on the right. I do it on every document. But again, coming back to your remark, in the query, I might have only 3 terms or 4 terms. So the query isn't that big. So it means that my query is in fact going to be quite sparse. It's a sparse vector in there. So in fact, I just, by convention, assume that my 4 terms are the first one. It doesn't have to be, but just for simplification. So it means that when I compute my inner product, I only need to really do a sum over four products here, because all the rest is 0 anyway. 0 times 0 is 0. So it means that, in fact, in spite of the dimension being super high, in practice, the sum is only the size of the query, the number of terms in the query. So that makes it actually already much easier in terms of computations. So that I mentioned, right, that we compute the cosine as renormalized, right? So that basically gives me this as a formula, the similarity between x and y. So these are xi and yi are my TF-IDFs, and then I divide by the cosine or the Euclidean norm like this, all right? Right, and again, this is something I will repeat and repeat and repeat. I took the TF-IDFs as an example. In practice, you can do a lot of different things. There's all kinds of variations that doesn't have to be exactly the TF-IDFs. There's many ways, but the most standard textbook way of doing it is with the TF-IDFs. Okay. Now, how do we do that? How do we implement that sum? Well, the good news is that we have this index, right? So we can use that as a supporting structure for our computations. We have the standard inverted index, but we need to slightly tweak it because I have the document frequencies in there, right? These are my purple boxes, so this is good. I have my document frequencies. This is also with the black letters, the black digits. And I don't have the term frequencies because this is, again, the standard inverted index. It was made for Boolean querying, so sets of words, I don't know how many times it appears. So I need to add it. And technically, it would be ideal if I could store the pre-computed TF-IDF in every posting. Basically, every posting that I have here, I would have the TF-IDF that corresponds to the term corresponding to the row and the documents, the number of which is the posting. But now, we need to be careful because we spent an entire week, last week, compressing the whole index using gamma encoding and so on, and that worked because we had sorted list of integers. But do you see that now if I start putting my TF-IDF in here, that breaks the whole compression scheme, right? So you need to be mindful and to be careful that you don't break things too much when you do that. So the way it's tweaked typically is that we are not going to put directly the TF-IDFs. Technically, what we are going to do is to store the pre-computed term frequency. It might need then that you cannot use the gaps anymore, but again, that there's many ways you can tweak that, but it's no longer a sorted list then if you alternate document ID TF, document ID TF, but at least it's still integers. So you can still encode that as a list of integers. And the IDF, well, technically the IDF, you could consider that you have the DF, right? So the DF gives you the IDF. What people do in practice, and frankly, I'm not exactly sure why, I can only guess, but what they store is in fact before the log. They don't take the log, they just divide n by df, and they store it as an integer. It's basically the rounding to the nearest integer of n divided by dft. Right, so they kind of pre-compute the division, but they do not pre-compute the log. Right. All right, but again, that allows us to treat that as an integer, doing it in this way. So this is my best guess of why we store n over df, but not the log of n over df, which normally the IDF would be. Who is with me? I'm throwing a lot of things at you, right? This is starting to be a bit formal. All right, so this is the document side, right? So these are the TF-IDFs of the documents. What about the query? Well, technically, for the query, it depends on the query, right? As the query comes, then we can compute the term frequencies in the query on the fly. And technically, it's a constant for the purpose of the computations we want to do. The query is just a given, right? It's we hold it as constant when we go over the documents. So what we are going to do is that we are going to now traverse in some way the standard inverted index, and we are going to compute the scores. I told you earlier, it's called evidence accumulation because we are going to accumulate the scores. And what makes it easy is that it's a sum. We compute the sum, this plus this plus this plus this. So all we need to do is have our buckets that keep track of the sum. And every time I see a new TF-IDF, I just throw it into the bucket, meaning that I add it to the current sum of the bucket. So every document, here I have 7 documents, so I have my 8 buckets. Every bucket starts with 0 and we'll keep adding the TF-IDFs, the products of the TF-IDFs. So you see now, this is the So yeah, it's unfortunate that the mathematical world is the same, but technically this is a term of the sum of the inner product, right? The inner product is the sum of these things summed over the terms for every document, right? So it means that I have, in a way, to look at every single posting that I find here. For that very posting, I have a specific document and term, and I have the query, so I can compute that term, that mathematical term of my sum. And all I need to do is put it in the corresponding bucket. So if D here is 4, I just add it when I come across it. I just put it in that bucket as a sum, plus equals in Java or C++. All right, so now really, the only question we have is in what order do we do that? Because it's bidimensional, right? I need to go through every posting, but there's rows and columns in here. How do I traverse the postings? Well, I can do it in different ways. One way is what we call term at a time. It means that I start with all the postings for ETH and I accumulate them. And then I take all the postings from Zurich and then all the postings for computer and so on. This is called term at a time. The other method is called document at a time. It means that instead I go left to right. I start with document 1, then document 2, then document 3, and so on, but for all terms. That would be close to the intersection and union algorithm, but on the entire set of terms in my query at the same time, right? By the way, you agree that when you do that, we only need to do that on the terms that are in the query. We are not actually doing it on all the terms, right? Because that would be zeros for the terms not in the query. So the number of terms that we sum over here is really just the ones in the query. Okay, so term at a time, document at a time. These are the two strategies, but you agree that the result is going to be the same because addition is commutative and associative, right? So it doesn't matter in which order I add. So this is why it doesn't matter if you do it like this or like that. The results will be the same. Let's do it then. So let's do term at a time, right? Imagine I have my query ETH Zurich computer. I have 5 potential documents that I need to rank. So here are my 5 buckets. No, sorry, 6 documents. Here are my 6 buckets. They are empty. And I'm going term by term. Let's start with ETH. So I have document 1. I compute the mathematical term of my inner product. So again, that's the product of the TF-IDFs renormalized by the length of the query and vector. That's this ugly thing in there, in the middle of the slide. So I increase the bucket counts, the bucket value with that. So I instead of putting a number in there, I just put I do it with the height of my rectangle in there, the height of the line. Then I do it with document 2, document 3, document 5, document 6. Term at a time, right? So I do it for ETH. I'm done with ETH. Zurich now. 3, 4. Oh, that's the first one. So 4 now is no longer 0. I'm done with Zurich, computer. 1, 2, 4, and 5. And now I'm done. So how do I know what to return? Well, document 5 comes first, then document 1, then document 6, then document 2, then document 4, then document 3. Do you agree? Let's check if we do this, if we find the same thing with document at a time. So let's do it document at a time now. So document at a time means I start with document 1. So again, I have my pointers that concurrently traverse together all the terms, but it's sorted, so it's exactly the same order everywhere. Think of the intersection or union algorithm. So 1 and 1. Now I'm done with document 1. Document 2. Again, ETH and computer, I'm done. Document 3, ETH and Zurich, I'm done, sorry. Document 4, Zurich and computer. Document 5, ETH and computer. And document 6, ETH. What are my results? Well, document 5, document 1, document 6. Oh, I'm so silly. I think I didn't draw it in the same way, but I should have. Yeah. I will fix that. I never noticed before that I didn't copy it over in exactly the same way. You know, it's fake, right? I didn't actually compute anything. It's just an animation. So when I'm done, yeah, I had 2, then 3, then 4, and here I had, it's not exactly. I'll fix that. Don't worry. It should be the same as the term at a time. Yes? Maybe we can just keep the habit of, yeah. and I'll increase the volume.
When you discussed the summing up gradually of that long term, if you can go back to that slide, there's two normalization factors. And to me, they don't seem trivial.
You mean the ugly thing in the middle, right?
Yeah, Q and D.
Yeah.
Q, you can just leave out, right? Because that's query dependent. But D, if you store it like this, if you don't store TF-IDF in your inverted index, then that's pretty hard to compute, no?
So first, with a query, you're right. The Q, the size of the query is constant. That you can drop. So you're absolutely right. Can you think of a strategy to take care of the document's length then? How can we optimize that?
I mean, I would store it on the side and then sum up the numerator of this term, and then at the end divide by it. But still, that leaves some overhead, right?
Mm-hmm. But indeed, you're right. That's the way to do it. Technically, you don't divide by D every time. You keep it aside. I don't know if I don't have a slide on that. Let me see. Can't remember. No, I don't, not yet. I have a slide later. So you're absolutely right that the document length, you only need to compute them for every document, but just once. So you could imagine that you store them near to the accumulators, just once. And then what you do is that when you compute the sums, you do it without dividing by the size of Q and D, just the products of the TF-IDFs. And at the very end, you multiply with the document's length what's in every accumulator, but just once at the end. So you're absolutely correct. It's a small overhead, but it's much smaller if you factor out the document size. So that's a very good point. Yeah, thank you. All right. Now, what do I do at the end? I have accumulated all my documents. I have 1 billion documents in there. And I need to basically now take the top 10. So I need to sort them and return the top 10. What's the complexity of that? Sorting the documents, returning the top 10. What's the complexity? Yes? You're already saying the correct solution. So let me say, so it is indeed O of n. You might have thought, or at least the first time I would have thought, it's O of n log n, because you need to sort the documents, right? So you might think, okay, that's n log n. But here's the trick. Think of the data structure you're going to use. There's many ways to sort documents, right? If you use a priority queue, you know, one of the ways is to use a priority queue. You can build that in linear time, O of n. But then to get the sort, you pop out of the queue one by one the documents, right, in decreasing. But we only need to pop out 10 of them. Imagine it's Google search, right? You return the top 10. So the priority queue I build in O of n, and then to pop out a document, it's logarithmic. So then I only need, it's a constant top k is a constant. So now it's k log n plus O of n, which gives us a linear complexity. Isn't that beautiful? O of n, we don't even have n log n. And again, that's because we only are interested in a constant number of documents at first, okay? So that is yet another optimization. Now, still have a bit of time, so let me just tell you, I'll probably continue on that last time, that's the end of this. Coming back to your numerous comments about all the ways you could construct your vectors, because you're absolutely right in all the alternatives that you suggested. And in fact, there's a whole restaurant menu. So this is the one we took. So you have a choice, for example, what do you do for the term frequency? Well, you could just put TF and that's it. That's what we did, in fact. But some other people instead use 1 plus log. And that is exactly what you suggested, just not with the square root, but 1 plus log. So this is something you can do. Look at the letter in the parentheses. That's the code for the choice. So N, that would be L. There is also something called augmented term frequency scaling, which is kind of just of a tilt of the curve. There are use cases for that, don't worry. People have a reason. Then there is the Boolean term frequency scaling. That means that we get back to the set of words. You don't want the numbers, you just want zeros and ones. Then just put a 0 or 1. And that's, now it answers your question you had earlier. For the query, we could do this. For the query, instead of TF, we just put a 1 if it's in there. Right. We also have this ugly formula that is yet another other way of dampening the whole thing. And again, there are use cases, people who want to use that formula instead, right? So these are all for the term frequency. You have all these choices. Now for the document frequency, you could say, I don't want to scale with the document frequency. For the query, for example, you could say, I don't want to multiply with the IDF. I just put a 0 and a 1 and that's it. So then you take the DF as just being 1 and that's it. Or you take the IDF, that's what we've been doing actually, log of n over df. Or you have this, what's called the probabilistic IDF. Why? I'll explain to you in a few weeks. But there is this alternate formula that is another way of computing the inverted document frequency. And then for the normalization, you could not normalize at all. That's if you want to drop the query normalization, for example. Or you could use the cosine normalization. That's the one we've been using. Or you could use the byte size normalization, just the number of bytes in the documents. Or you could use a tilted curve. Again, people have reasons for that, has to do with smoothing and so on. So you could use instead this, slightly pivot. And that's it. And that gives us the smart notation. You just need to pick the letters that corresponds to your choice. And technically, you have 6 choices. You have, I never remember if it's the query here, the document there. So forgive me for this, but let me, the document on the left and the query on the right. Yeah. So this is what you pick for the term frequency scheme for the document. This is what you pick for the IDF scheme for the documents. And this is the normalization scheme. And then for the query, this is what you pick for the term frequency. This is what you pick for the IDF. And this is what you pick for the normalization. So basically, you just need to pick the letters in here and assemble this. It's like going to the restaurant and asking for your menu for the starters, the entree, as they say in California, and then the desserts. And that's exactly what you get in here. That is called the smart notation. And again, that answers the question when you say there's many ways to do it. Yes, absolutely. There are many ways to do it. And in fact, it's even standardized in this way. Okay. That's my last slide. This is it. Now we can go grab lunch. Enjoy the exercise sessions. Do not forget to submit your quiz. We even gave you until 3 p.m. The TA team gave you until 3 p.m. So do it, and we'll see you in the exercise sessions and next week at 10 a.m. Thank you very much, and goodbye.